Hello everyone. In this session, we are going to learn about the random search algorithms. In comparison with the deterministic methods that we have been learning till now, this method is of stochastic type. In this session, we will learn the differences between the deterministic and the stochastic methods. We will see some of the features which make the stochastic method different than the deterministic ones. We'll see the basic random search algorithm in more details, and finally we'll apply the random search algorithm to solve a nonlinear optimization problem with constraints. Let's proceed with the differences between deterministic and stochastic methods. The deterministic methods, as the name suggests, are based on a fixed strategy. That is, if one starts with a specific initial point, the final destination of this method is usually fixed. In this method, one starts with a point within the search domain and proceeds systematically to approach towards the minimum. For certain type of problems, these methods guarantee exact solution. However, this is not a universal rule. Examples of deterministic method are Cauchy's steepest descent method and box method, both of which we have covered previously. The stochastic methods, however, include an approach which is based on principles of probability. These methods start with random sample of points. These points are systematically manipulated to travel towards the minima. Some of the examples of random search method are the simple random search, which we are going to discuss in this session, and the genetic algorithms, which we are going to see later. Here are some of the features of stochastic algorithm. In general, these methods find all local minima within the search space with better effectiveness than the deterministic methods. Generally speaking, we start with a set of sample points which are randomly chosen within the search space, usually considering a uniform distribution. That means any point within the search domain has got an equal probability of getting selected in comparison with the other points. The computations on these points are used to effectively locate the region of attraction. The region is such that the searching from any point within this region always leads to the same minimum. Another feature of stochastic method is that these methods yield different minima when run repeatedly. Hence, a number of runs are taken to establish the global minima of a problem. Before we proceed further, let's understand how the random search algorithm fits into the overall scheme of algorithms we have studied yet. Obviously, the random search algorithm is a numerical method. The implementation of the method that we are going to see is as applied to constraint problems. Note that all the algorithms that we have previously seen, they correspond to the unconstrained problems, except for the simplex method, which is an example of constraint problem. There are many variations of random search algorithm. The one which we are going to study is the one proposed by Luce and Jacola. This is a very simple approach, very easy to understand. However, it is not efficient, and there are better algorithms available which are little more complex than the one which we are discussing. Let's understand the algorithm with respect to a two-dimensional problem. So I'm considering an optimization problem in terms of two variables, x1 and x2. As in all random search algorithms, you initially pick up a point. So let's say this point is x0, which is having coordinates x01 and x02. The algorithm requires you to choose a range or the search space about this point. So we are going to define a search space in terms of a parameter z, which is equally distributed. So here we are having z0 1 by 2 and other side z0 1 by 2. Similarly, on the second axis we have the z0 2 by 2 and z0 2 by 2. So this defines our search space. In the first part of this algorithm, we are going to create a certain number of randomly generated points within this search space. So we will define some randomly generated points which are within this search space. Now understand that this problem is that of a constraint type. So some of these points will be violating the constraints. So for example, let me see that this is one of the constraints and this is second constraint. We will find that in this case 2 points are violating the constraint and these points need to be recreated. So after creation of every randomly generated point, we have to see whether the point satisfies the constraint conditions. If not, then we have to recreate this point. So in this case, 2 points need to be recreated, and let's say those 2 points are recreated so that the required number of points are available in the search space. The next step in this algorithm is to locate the point which is having the least value or minimum value amongst all the points, including the initial x0 point. So including the point x0 and all the other points, we have to find out which is having the minimum point. So let's say our minimum point is the one as located here. So this becomes the starting point of the next iteration or x1 point. Around this point, we have to create a new region for searching. The size of this new search zone is smaller than the one that was previously. So if the previous zone was having size of z0, the new one will have a value which is z1 equal to some reduction parameter multiplied by z0. The epsilon in this case is the reduction parameter which defines that after the previous iteration, how much reduction in the search space should be there in the subsequent algorithm. So in the second algorithm, we will have a search space which is shorter than the first one. So this is the new search region which is smaller. Now within this search zone, we have to create the new randomly created points. If any of these points cross the constraint conditions, then we have to recreate these points, and this process is continued. This entire procedure is given in the form of flowchart as shown here. So this flowchart defines the various parameters involved and it can be directly converted into computer code for doing the calculations. Before we proceed for the numerical problem, let's understand the terminology used in this algorithm. So x0 bar is a vector of the initial point. Remember that this is a multivariable case. So for 2 dimension, we have x0 equal to x1 and x2. For 3 dimension, we have x1, x2, x3 and so on. For each dimension of the design variable, we have the range parameter which is z. The superscript of these parameters, they indicate the iteration number. So for first iteration, it is x0 and z0, and subsequent iterations, this number will keep on increasing. The n is the design variable space, that is how many design variables are there in this particular problem. The p is an important parameter which defines how many points, random points, you are going to generate within each iteration. And after each iteration, you are going to reduce the search space as we have seen in the illustration. So the space reduction parameter is epsilon. So each of the dimension of z will be reduced in the subsequent iterations by using the parameter epsilon. As this is a numerical method, we have to keep some upper bound. So the parameter q defines how many maximum number of iterations you are going to do. And the subsequent steps of this algorithm explain the procedure which I explained graphically a few minutes back. Now let's apply this procedure to an actual numerical problem and see how it works. Let's illustrate the algorithm by an actual problem. In this case, we want to optimize the objective function, which is the well-known Himmelblau function, which we have used in previous cases. The constraints are as given, and as you can see, they are of nonlinear type. The first step in the algorithm is to choose the starting point and the starting range, both of which have been specified. The number of iterations, the number of points which are to be generated during each iteration is specified as 3. Note that this is a too small number for illustration purpose. In general, the p is greater than 100. The number of iterations have been specified as 10, and the space reduction factor after each iteration has been given as 0.25. Again, this number is very large. Typically, the value of epsilon is in the range of 0.05 or smaller than that, so that a better convergence to minimize obtained. In order to solve this problem, starting with the initial point given and the search space that is defined, we have to create 3 number of random points within the search space. The second step of the problem is to generate the 3 number of randomly distributed points within the search space and to check that these points are satisfying all the constraints. So after doing the calculations, the 3 points which were calculated are as follows. So the first point is 4.018 and 1.817. The second point is 2.856 and 0.026, and the third point of first iteration is 1.607 and 1.700. It has been checked that all these 3 points satisfy the constraints which are specified, so they are valid points. For each of these points, we calculate the value of function. So value of the function for the first point is given as 49.38. For the second point, the function value is 25.095, and for the third problem, the function value is 51.375. When you are locating the minima, you have to also consider the initial point that was considered, which is in this case 3, 3, for which the function value is equal to 26.0. So among all the points that have been evaluated, we find that the minima occurs at the second random point and the value is 25.095. So for the next iteration, the starting point would be the second point and the new range would be given as 1 minus epsilon times the initial range, which turns out to be 4.5. So we'll start the next iteration with 2.856 and 0.026 as the starting point and 4.5 as the search space range. These calculations are repeated for 10 number of times till we reach the final solution. Since it involves a lot of calculations, I use spreadsheet to do these calculations. The next screen shows the results from this spreadsheet. In the spreadsheet solution, the columns are representing the iteration numbers. So you have iteration number 1, 2 and so on up to iteration number 10. In the first iteration, we started with x1 and x2 as 3, 3 and the values of z, that is the space for searching, is 6, 6 in the 2 dimensions. As we have seen in the previous screen, the best point was found to be 2.856.026 and the reduced space is 4.5, 4.5 and the function value was 25.95. In the second iteration, the starting point is 2.856 and 0.026 with search space as 4.5, 4.5 and we get the new points and the new search space for the third iteration. As we continue this process, you will find that in the final iteration, we get the value of the minimum point or the candidate minimum point as 2.990 and 2.082 and the value of function is 0.105. If you plot the progress of these calculations after every iteration, you can graphically represent it as shown here. So we started with a point which is 3, 3 and in the next iteration we have gone to another point. In the subsequent we have gone to next point, then to another point, then to another point, then another, and finally we reach the destination which is 2.99 and the other point is 2.0 values. So this is an minima which is found out by this random search method after 10th iteration. As you can see, if we perform these calculations with higher number of random points and a smaller value of epsilon, we'll get a better result. If we compare with our previous results, the optima for this function is 3, 2 and we are quite close to that point at the end of 10th iteration. But this is not guaranteed every time. If you take this run on your computer, obviously the random numbers generated will be different and you get different results at the end of 10th iteration. So that is a characteristic of the stochastic methods, that the final result is not accurately guaranteed. You will get close to whatever results can be obtained. Okay, let's recap this session. In this session, we have covered the difference between the deterministic and stochastic methods. The stochastic methods start with an initial set of randomly created points and then proceed to manipulate these to achieve the minimum. The stochastic method in general give better results about multiple minima than the deterministic methods. However, the true minima is in general not guaranteed in stochastic methods. The basic random search algorithm discussed here is an implementation for constraint optimization problems. There are many more variations of this technique available which are more efficient. The choice of number of random points and the region checking parameter are important and they significantly affect the performance of this model. I thank you for your attention and time. Bye everyone.